So after many years of leading, illustrious years of leading the full-scale tunnel, the vertical spin tunnel, the drop model test technique in cutting-edge research and technology development that was nationally and internationally recognized, Joe moved on to other important leadership roles in flight research and in systems analysis, where he was equally successful. And for all these accomplishments, Joe received numerous awards and has presented invited lectures all over the world. But after a very productive 36-year career, Joe retired from NASA and started a second career doing historical research on Langley. And the result of these endeavors are 7 fascinating books, NASA publications on a variety of aeronautics topics. And his latest book that he's currently working on is the basis for the lecture that we're all about to hear, with the title as you see there. And I know we're all very much looking forward to reading this book and to hearing Joe's lecture today. So without further delay, let me turn the podium over to our speaker, Joe Chambers.
Thank you, Luad. Everybody hear me? He didn't tell you the part that I won all the card games. That's why he was so great with his comments. When Gowdy called me and said, Joe, would you mind coming out and talking about the full-scale tunnel? I said, don't throw me in that briar patch. No, please don't do that. This is my favorite topic, of course, and I want to thank the Colloquium Committee for inviting me out for this, and I hope you'll enjoy the presentation. It's pictures, it's movies, there's no equations, there's no word charts, so enjoy. This year, the NASA Langley Research Center is celebrating its 95th anniversary. And as Langley continues to undergo inevitable and dramatic changes in the missions and the culture, the facilities, it's extremely appropriate, I think, to reflect on the great legacy of this research center. And today we're going to talk about a facility that certainly is embedded in the most intimate history of aviation in the United States. The full-scale tunnel went into operation in 1931 as the world's largest wind tunnel. It was the first tunnel capable of testing powered full-scale airplanes. It completed its last test program in September of 2009. After almost 80 years of continuous service to this nation. Over its lifetime, I counted a total of 1,564 tests of individual test subjects, many of which were critical to the interest of the United States, both militarily and in the civilian world. Housed in a building longer than a football field, the tunnel was visited by many of the most famous people in the history of aviation and others who were awestruck by its massive size. The full-scale tunnel was demolished last year, but will live on forever for its impact and contributions to aerospace technology. About 3 years ago, the opportunity was presented to me to write a book about the history of the full-scale tunnel. Which, of course, I completely leapt at, and was able to get into archives, old reports and things that had never been really analyzed, discover a lot of information that had never been documented. And what I'm going to present today, for those of you not familiar with the facility, I think will be impressive. For those of you that are familiar with the facility, I'm going to surprise you with some things that I found out that happened there that you don't know about. So I'm hoping that you'll be entertained by this. The book draft is completed. It's up at NASA headquarters now in the queue waiting for printing. There's over 400 photographs, close to 500 pages, and several hundred references for those that want to get into more detail relative to the facility. At this time, the book is not published, and I'll close the presentation with some comments on the projected schedule for its release. The presentation, as Luad said, is based on selected excerpts from the book, and at the onset, I want to apologize on two counts. The first is my comments are going to be very brief in view of keeping us constrained to our time today. And the second is, if you're a fan of the full-scale tunnel, I apologize if I don't mention your favorite topic. The next slide is going to show the outline of the presentation. What I'm going to try and do here in the next hour is to discuss how this tunnel came to be in terms of the politics and mechanisms that originated the tunnel, and some of the birthing pains that it went through as it went into operation. We'll spend time talking about the war years and World War II, when it served the greatest generation, and it's probably its greatest legacy. Talk about the post-war years and what happened immediately after World War II, and after the Sputnik event, how this old wind tunnel designed to test biplanes fit into the nation's space program. In the mid-90s, NASA declared the facility to be non-relevant to its mission, and it was an arrangement was made for the Old Dominion University to operate and manage the facility. I'll discuss some highlights of those years, and then I'll close talking about the end of the line in terms of the final closing of the facility, the demolition of it, what we've done in terms of artifacts from the tunnel and where and when they will go on public display. And then I'll talk finally about the book and when you can expect to see the book. During rehearsals, this ran about an hour. I hope you'll stay with me during that hour. I promise to keep you entertained. You keep your eyes open. The story of the full-scale tunnel starts with a deplorable situation in the United States. There was almost total lack of interest in aviation in this country, the country that invented heavier-than-air flight. When World War I started, the European nations, France, Germany, England, all had over 1,000 aircraft. The United States had 23. Alarmed by this whole situation, a number of notable scientists, Alexander Graham Bell, Charles Walcott, who was the secretary for the Smithsonian Institution, and others, advocated strongly to Congress that we needed to do something in the United States to organize the progression of aviation. In 1915, without any great ado, Congress approved formation of what was called the National Advisory Committee for Aeronautics, or the NACA. And with the establishment of that committee, it was to be manned by a group of 12 presidential appointed individuals who served with no salary. And in this day and age, I have to say they had no year-end multi-million-dollar bonuses either. The facility, a research facility, was also an option when they formed the NACA. Well, it didn't take very long for the members to say, we need a research facility. So in 1917, this area was acquired by the War Department for a research laboratory. Now, tonight I'm going to be talking to people who aren't familiar with the background or the location of these facilities, so I'm going to present this orientation, compliments of Google, that will enable people to understand the location of Langley Air Force Base, surrounded by the Back River, which I'll be mentioning quite a bit this afternoon, North Olmsted, Commander Shepard Boulevard, the current location of the NASA Langley Research Center, which is on property, in fact, that was acquired by the War Department in 1939. But we're going to be talking about an even earlier period over on the Langley side of the base. This area was the area that Congress had assigned to a combination of the Navy, the Army, and the NACA for operations. The Air Force quickly moved or the Army Air Forces quickly moved their center of research out to Dayton at McCook Field. The Navy moved out with its research activity to the naval activity at Norfolk, but the NACA stayed. By the way, in the first year, the NACA committee wanted to move away from Langley and proposed to Congress that it do so, and Congress said, no, you're where you're going to be. So that's where they ended up. Now, let's take a closer look. Take a look at where the original NACA buildings were in the Air Force side of the base. For orientation, obviously the main drag main road through the center, through the Air Force Base. Dodd Boulevard is here. The yellow circle were the original NACA buildings, and many of them are still standing today. And you can see where the full-scale wind tunnel was located in this area as well. So we'll be talking about those activities as well. In 1924, the laboratory had been founded and put into operation. What you see here is the main administration building. 2 wind tunnels were housed in these buildings. Dodd Boulevard, by the way, is in the front of the administration building. And I want to call your attention to these 2 buildings because they played a role in the development of the full-scale wind tunnel. Originally, these were 2 engine dynamometer test sites and were used in the early days, in the early 20s, for testing. But they'll come back in our story in just a minute. In the late 1920s, the NACA got an urgent call from the military who were very concerned about how to reduce the drag of the exposed radial engines in vogue at the time. And the NACA proceeded to build a facility known as the Propeller Research Tunnel. It had a 20-foot test section. As you can see, the test throat was open to facilitate moving airplanes and airplane components into it. You can also see that it wasn't quite large enough to test a full-size airplane, but at least they could put the engine and the power plant within the facility for testing. The laboratory engaged in a so-called cowling research program, which developed a series of configurations of rings and various nose shapes around these exposed radial engines to dramatically reduce the drag of the airplane, in some cases by as much as 30%. Industry went wild with the results. The NACA cowling concept was applied to most of the aircraft in that era, including aircraft like the DC-3 and others. In recognition of the application of that concept, the laboratory won its first Collier Trophy, and I believe a replica is in the display case in the back of this room. It created a great deal of excitement within industry and within Congress. Lindbergh had just made his flight in 1927, and Congress was just absolutely wild and ecstatic over the promise of aviation, and in particular this laboratory called the NACA lab. Now, I want to switch from that history and talk a little bit about more detail of what led to the full-scale wind tunnel. This picture has a number of very important historical people in it for the Langley Laboratory, but I want you to focus just on the 3 that I've highlighted here. Max Monk was an immigrant German who was hired by the NACA, a brilliant scientist who came up with the idea of a pressurized wind tunnel. That pressurized wind tunnel won worldwide recognition and acclaim and put Langley on the map. That facility is outside this building on the grounds of the Reed Center and available for inspection. But Monk was an aggressive, arrogant individual, and no one on the Langley staff liked the man very much. But he had a sway with management at that time. Now, the young fellow in the back, Elliott Reed, was a brilliant, absolutely brilliant aerodynamicist. He, by history accounts, ranks up there with Dick Wickham and others. He was a brilliant experimentalist, and during the construction of that propeller research tunnel, he begged the question of the senior staff, why not build a wind tunnel large enough to test a full-size airplane? Why limit it to 20-foot test section? Which immediately plunged him into a huge argument and debate with Max Monk, who was adamant, no, 20 feet is enough. We don't need a full-scale tunnel. Elliott Reed was livid. This and many other arguments that he had with Monk finally drove him from Langley. He left Langley a year later to Stanford University, where he assumed a full professorship based on his contributions at Langley at the tender age of 27. Elliott Reed was one of the most loved, impressive faculty members ever at Stanford University. And I want you to remember that he was the first person to ever beg the question, do we need a full-scale wind tunnel? Now, both of these individuals, Max Monk was driven off by management that same year that Elliott left. But I want you to take a look at this fellow on the right, George Lewis. George Lewis was the head of the research program at NACA headquarters. He loved Langley. He came to Langley every week. He didn't want to meet with the center director. He wanted to meet with, quote, my boys in the facilities. He heard Elliott Reed's plea. He was aware that Congress was very receptive to new ideas, and he personally advocated and pushed the system for the new full-scale tunnel. The members of the NACA approved George Lewis's advocacy, and Congress enthusiastically supported the proposed facility with funding that began in 1929, just at the beginning of the Depression. Of course, the manpower was quite available during the Depression years and helped in terms of the construction of the facility. This is a photograph of the first staff of the full-scale wind tunnel. I could speak an hour about each of these individuals. I'm just going to say a few words, hopefully, about each. The project of building the tunnel came under the management of Smith de France. He came to the wind tunnel group from being a test pilot here at Langley in the early days. In the 1940s, he was selected to be the first head of the new NACA facility at the Ames Laboratory in California. Clint Dearborn was the second head of the full-scale wind tunnel. His claim to fame is in World War II, he headed something called the Cooling and Cowling College. This was a unit at Langley based in a special building wherein industry and the military would send their people TDY to come in and be exposed to the Langley experts in terms of these two subjects. Extremely productive, resulted in many cooperative activities, and was very akin to what happened here at Langley in the 1970s when the Boeing company sent a team to take a look at what we were doing in flight displays on jet transports, leading to the adaptation of the glass cockpits in current-day jet transports. The third person I'd like to talk about is Abe Silverstein. Abe Silverstein never took a formal aerodynamics course, but he was a brilliant mechanical engineer. He knew heat transfer and he knew engines, and he led the way over at the tunnel in his later years in terms of cooling work. After his days here at Langley, he was personally selected by Lewis to go to the new Aircraft Engine Research Laboratory at Cleveland in the 1940s. He worked there in new jet engine technology. He was later called to NASA headquarters when NASA began to plan its space program. Silverstein led a group in that activity, and he personally named Project Mercury and the Apollo project as well. After the Apollo assignments, he returned to what was then the Lewis Research Center and ultimately became the center director at Lewis. Now, two other people became, in the early days of NASA, very prominent. In 1930, Harry Gett joined the tunnel, later became the first director of the Goddard Space Flight Center. And in the 1970s, Delma Freeman, a good old Pocosin boy, worked the tunnel, and he later became director of Langley in 2003. So no other facility in the history of NASA can claim that it had 4 center directors come from within its bowels. I think that's remarkable. Now, let's talk about how the tunnel was formulated. The first problem that these poor people had was this was a gigantic tunnel. It was much larger than anything anybody had ever attempted to build, and it would require at least 2 propellers. No one had ever done detail work on that type of configuration. So the first request from the group was, we need to build a model of this wind tunnel. 1/15 scale. Management's reaction was, great, we approve it, but by the way, we don't have any shops that can contain such a big model. You'll have to build it somewhere, maybe out of doors. And to show you the kind of NACA spirit that existed, after a great deal of research, I found that this was where they decided to build that model tunnel, between the 2 engine dynamometer buildings. An area was built with plywood and covered with canvas, and the testing was done in that facility, particularly to check out the power requirements that would be required for the new tunnel. After getting data from that model tunnel test, DeFrance and his team entered the final design of the full-scale tunnel. And this layout shows what the facility looked like. It was gigantic, longer than a football field. You can see the test section, as was the case for the propeller research tunnel, was open throat. Air was drawn through this 30 by 60 foot test section by two 4,000 horsepower electric motors, each of which had a 35.5 foot diameter four-bladed propeller. After going through the test section, the air was routed back through the walls of the building in what was called a double return type wind tunnel. There were roll-up doors immediately adjacent to the test section and also on the exterior of the building to permit the entry of airplanes during the test program. It's important to note that outside of the flow circuit in this tunnel, there was ample space for other activities. For example, all of the office spaces for the engineers were down below the return passage. And through the years, there have been a large number of research activities of importance that did not require the airflow that were conducted in this building. Those are revealed in the book as well. The top speed of the tunnel was to be about 110 miles an hour. Electric power was provided by the city of Hampton. And the city said, now just a minute, if you're going to operate in daytime, you're not going to run 110 miles an hour. So the speed was limited to only 50 miles an hour during daytime operations. This cross-sectional area of this wind tunnel, to give you a feel for the size, was no less than 5 times larger than the second largest wind tunnel, which was the propeller research tunnel. So it was indeed a huge facility. The construction of the facility commenced, and to the uninformed, this looked like someone was building a building inside out. All of the steel support structure was on the outside of the building. The inside of the building was lined with corrugated, asbestos-impregnated cement sheets to provide a smooth airflow within the test circuit. These sheets were known as carry stone, and they were remarkably robust. They were used in a lot of the Army Air Service buildings and in the early NACA buildings. Those that were part of this full-scale wind tunnel, a great number of them lasted the full 80-year life of this facility. Very impressive in terms of their robustness. By October of 1930, the facility, the outer walls had been constructed, awaiting the drive system and the propellers. The funding for the facility had been $1 million approved in the federal budget. The facility was completed and money was returned to the Treasury. $250,000 of that $1 million went back to the Treasury. I can't imagine that happening today, but the tunnel had proceeded in construction with an absolute mandate by George Lewis that it would be completed within a year and be available for dedication in May of 1931. DeFrance and his people worked frantically trying to meet that schedule with such an immense job, trying to get everything ready as the dedication date approached. Finally, on May the 27th, 1931, a dedication ceremony was held. Vought and the Navy contributed a O3U biplane Corsair for the testing, and I want to point out some of the features of the facility before we talk about what happened. You can see that the airplane is mounted on struts to a free-floating frame, which in turn is mounted on Toledo scales. The aerodynamic data were measured by a push-button action, which printed values of the scale readings out on cards, and data had to be reduced by hand after that. If you look carefully on the far side, down at the bottom of this wall, you can see an individual. He was the tunnel speed control operator. And he stood at a console with a speed control lever very similar to a streetcar lever and controlled the airspeed in 24 steps during the whole process. And if you also look very carefully, you can see up in the cockpit a test engineer for that day. He must have been the junior employee at the time. But his job was to start the engine during the test and the demonstration that was to be held by the visitors, for the visitors. An invited crowd of about 100 dignitaries, particularly the media, were invited. Joseph Ames, who is the chairman of the NACA, gave a few glowing comments about the future of this facility, and Smith de France described what they would see. Now, during the demonstration, this being daytime, the tunnel came up to a speed of about 50 miles an hour, and the angle of attack and power were varied. Very impressive display, and after the short demonstration, the media was absolutely awestruck. They ran from the building to notify their readers of this impressive example of the supremacy of American ingenuity in aviation, and quickly called this thing the Cave of the Winds. After the crowds departed, this was a Wednesday afternoon, de France and his crew began preparations for testing this airplane the following Monday. And to my utter amazement, there has never been documentation of the chaos and trauma that happened during the following week. When the tunnel was operated near 100 miles an hour, this biplane began to shake and buffet to the point where there was great alarm as to whether it would stay on the mount system. And testing was just totally unacceptable. It was obvious to everybody that something had to be done about the flow in this tunnel. It was much too turbulent. So for 3 months, the full-scale tunnel went down for repair and modification. The biplane was removed from the test section, never to return to the full-scale tunnel. And in this picture, you can see, bless his soul, riggers in there with wooden ribs to form a second skin to increase the curvature in these corners where the flow separation problems were really occurring. So a second skin was put in the full-scale tunnel. And a little story, one of the older mechanics, when I first came here, told me that the mechanics during World War II found out that was an excellent place to hide their whiskey bottles, in the open space between those two skins. After working all summer trying to get the tunnel in a low turbulence condition, the tunnel was open for business. Abe Silverstein said it in his memoirs, to his amazement, there was no research plan for the tunnel. George Lewis's idea was field of dreams, just build it and they will come. And it didn't take very long before they came. The very first test in the full-scale tunnel is one that really hasn't been documented. It involved an entourage of the government, military, industry officials in a high-priority job involving a lawsuit. It turns that there was a Frenchman by the name of Robert Isnault-Peltier, who, before World War I, spent most of his wealthy father's money designing airplanes and trying to control them. Spent a great deal of his father's money. He filed a patent claiming that he had invented the joystick. Interesting story. After World War I, he filed a lawsuit against all French aircraft manufacturers. Huge amount of money, and he became a very, very wealthy man. He also tried to sue the British, but he could not due to intergovernmental activities. In the United States, he claimed a lawsuit against the U.S. government, Vought Company, the Navy, and the Army. So in September of 1931, quickly, those entities requested tests in a full-scale tunnel to disprove his patent and show that, as he put it, a single stick could control the airplane. Now, for you technical guys out there, this is kind of interesting. He had the right idea, except he had two levers in his airplane, two sticks. One, for some reason, he used to control the ailerons, but the other controlled both the pitch and rudder surfaces. And he had interconnect those surfaces on a ring, so that if you move the stick, you get elevator, rudder, and you're moving the ailerons with the other stick, and yet his patent claimed a single stick movement would control the airplane. Well, the staff of the full-scale tunnel said, we will disprove the validity of that claim, did testing of that facility under high priority, and the New York court and the New York Court of Appeals both disproved or dismissed the claim. The Department of Justice sent a letter to the NACA saying, you have a fantastic facility, and furthermore, Smith de France was our outstanding witness to win this case for the United States government. Unfortunately, as happens a lot these days, 6 years later, Peltier appealed his case to the U.S. Supreme Court, who dismissed the earlier court's decisions and awarded him $1 million in 1938. That was the first test. By the way, Peltier, after he finished with his aircraft interest, became interested in astrophysics and ultimately became a very, very acclaimed individual of that community. Now, I want to change to another interesting topic. In 1926, George Lewis quickly saw that it would be important to get the word to the industry and the world regarding what was going on here at Langley in research. So he began a series of what were called engineering conferences. Every year, once a year, attendees would be invited to come to Langley, hear briefings on the technology, and in turn, give their briefings on what research they felt needed to be done. This particular picture, which was taken in 1934, in my opinion, is the most historic picture ever made, certainly at Langley, if not in the area of aviation. The attendees here are posing beneath a P-26 pea-shooter fighter airplane that was in the tunnel for testing. And these are true legends of the U.S. aviation history. The 245 people that attended this conference were among the most famous ever in our industry. Unfortunately, this picture, which is now 78 years old, they didn't attempt to match the faces with the people. But I had the time in writing this book to use face recognition software in today's world to be able to identify some of these people. And I'm going to have a little audience participation. You can see if you can recognize. I'm going to show you close-ups of the left side of this picture and the right side of the picture and say a few words. You think about who they might be. I'll tell you who they are. So let's start with the left bottom. I'm going to start with the father of it all, Orville Wright, who at that time was a member of the NACA 12-man committee. Sitting next to him is Charles Walcott. He was the guy that we all should thank for the formation of the NACA from the Smithsonian. Here's Lucky Lindy, Charles Lindbergh. Below him, this is Reuben Fleet, who was the founder of Consolidated Aircraft. They would later build 18,400 B-24 bombers during World War II, the largest single military production ever for the United States. Over here, Spruce Goose, Las Vegas, Howard Hughes, in those days working for the Fairchild Company. Over here is Al Mooney. Those of you with general aviation interest certainly know who he was. Here is the designer of an aircraft in World War II known as the bent-wing bird. The Japanese referred to it as the Whistling Death, the F-4U Corsair. This is Rex Beasel of Chance Vought. This is Edward Warner. He was the editor of Aviation magazine, which fought very, very hard to keep the NACA alive within criticism in those days. And here, I'm sure many of you can recognize this fella. This is Flying Wings, B-2. That's Jack Northrop. Now let's take a look at the other side of the room. Let me orient us. Here's our friend Orville. This is Joseph Ames, the chairman of the NACA. This is Admiral Ernest King. He was commander-in-chief of all U.S. naval operations, Atlantic and Pacific, during the war years. Over here, rotorcraft, wop, wop, wop. That's Igor Sikorsky. This is our good friend George Lewis in the middle of his cohorts. The first designer of blended wing body configurations. This is Vincent Bernelli, who had that design concept back in the 30s. Up here is Sherman Fairchild of the Fairchild industry. A man down here whose name is synonymous with Wildcat, Hellcat, Tomcat. This is Leroy Grumman. Over here in the dark suit with a little bit of hair on his head is an individual who 8 years later would win the Congressional Medal of Honor for his B-25 raid on Japan. This is Jimmy Doodle. And here is an individual I really want you to remember. This is Walter Deal, a brilliant aerodynamicist from the Navy, Bureau of Aeronautics. He was a tremendous force in this center getting work during the early days of World War II and a true advocate of Langley. So you can see why some people have said, you know, Joe, if that B-26 would have fallen off its mount and killed the attendees, the United States would have lost World War II. The early days in those 1930s, these are the types of things that were done in the tunnel, and I won't take a great deal of time to discuss them. It was built in part to understand how to go about scaling small-scale models to full-scale test conditions. So, for example, a number of different sized wings would be run in the tunnel and results compared to help guide researchers in other wind tunnels. In the early 1930s, there was a tremendous number of tail failures of military aircraft. Jimmy Doolittle became a major part of that investigation, and the tunnel itself was used to measure tail loads led by the structures group here at Langley. Lift devices were a major part of their activity. The P-26 in its original form did not have flaps. It was the first Army monoplane, and it was a hot little number when it came in for landing. So work from the facility were ultimately put on the P-26 as well. And over here, Langley engineer Fred Wyke, who's widely acclaimed and famous, had designed aircraft with safety in mind. This is the Wyke W-1A being tested in the facility, notable for its safety features, but also the fact it was the first airplane with a steerable tricycle gear. And from this, of course, the Lockheed P-38, other aircraft in World War II, adopted that design, and today virtually all of our aircraft use that design. At the end of the 1930s, people began scratching their heads saying, well, that must be the end of the full-scale tunnel. There's nothing else to be done. And then there was a phone call from Walter Deal at the Bureau of Aeronautics. The Navy had just contracted for its first monoplane with a company called the Brewster Company. Brewster had previously been experts in building horse-drawn carriages, but they had little experience in aircraft design. Nonetheless, the Navy awarded a contract for what was to be a 300-mile-an-hour fighter. The European fighters at the time in Germany and England were well above that speed. This airplane in its early flight trials by the Navy could not exceed 250 miles an hour. Walter Deal says, send it to Langley, and let's see if any way we can fix the airplane. You can take a look at the construction techniques. You can take a look at the exposed landing gear wheels, and you know this is going to be a problem right off the bat. So the airplane was flown to Langley and remained in the full-scale tunnel for about 5 days while the engineers took a look at it. Now, this is a video clip from a movie made during those tests, and I'm hoping that you'll be able to appreciate just how bad this airplane was. You can see the wool tufts that have been attached to the airplane to show the airflow and its relatively steady and its relative steadiness. And you can see the cracks and the crevices and the exposed rivet heads and doors, access doors, and what have you. And up front, the airplane really had some problems. The carburetor intake, machine gun ports, etc., had been apparently haphazardly put on the airplane, and it had a gun sight as well. Now, if you look at this view of the carburetor intake, we have an area of completely separated airflow in which the flow is actually forward on the airplane. And you can catch this in many of the locations along that cowling area. So there were a lot of lessons to be learned by not only Brewster, but other aircraft manufacturers when they took a look at what happened to the Buffalo. After 5 days of operation, the NACA staff at the tunnel had identified different modifications to the aircraft that would enable it to increase its top speed by about 35 miles an hour. Not up to 300 yet, but well on its way. The military quickly caught on to this game and decided all of its prototype aircraft had better come through this wind tunnel during World War II. This aerial view put in just to show you the convenience that was there for the NACA operation. Up at the top, you can see the flight hangar that was used for flight testing and evaluation of aircraft. Down at the bottom, you can see the location of the full-scale wind tunnel. So typically, the military would fly an airplane into Langley, into the flight hangar. It would undergo evaluation for handling qualities or performance, whatever. And then it would be towed down the street to the full-scale tunnel, the same airplane, mounted on the struts, and be tested for analysis and further correlation with the flight testing as well. The field, I need to go back here. You'll notice the brightly colored Army hangars and the NACA hangars that were there. This picture was taken in 1939. That changed dramatically during the war years. With German submarines off the coast and in the bay, it was decided to camouflage all of the east area of Langley Field. The Army appropriated $500,000 to paint most buildings a deep shade of green. And this shows the relative look at what full scale, the vertical spin tunnel, the old 19-foot pressure tunnel, the forerunner of the current day transonic dynamics tunnel, looked like during 1943. And here they came, all of the aircraft. I'm not going to show all the pictures because there's a bunch of them, 40 plus. But let's take and talk about the Navy aircraft first. The Navy was one of the first customers of the full-scale tunnel, thanks to Walter Deal, and in fact got to the source first before the Army, and ran through most of their aircraft in an early stage. Those Brewster Buffalo tests changed their attitude, and this became part of their development process. The Army was livid. The Army couldn't get into the full-scale tunnel because the Navy was taking so much of its time. In fact, they stationed a liaison person here at Langley in 1939 with the orders to get into that wind tunnel. They were at the point of complaining to the NACA that they should change their name to the Naval Committee for Aeronautics. Nonetheless, they did make it into the tunnel. You can see some of the famous aircraft there from World War II, ranging from the early P-40 designs to America's first jet airplane, the YP-59. So in addition to Army and Navy aircraft, I want to point out that they tested a number of unconventional airplanes during the war. These didn't make it into production, but they're historically very significant. I won't go into the details. They'll be in the book, but there were certainly remarkable entries with very interesting test programs. Down at the bottom, I've included this picture of the first military helicopters, this is Sikorsky YR-4B, to indicate the fact that the full-scale tunnel was very active in terms of testing rotorcraft during its earlier days as well. Now, let me conclude the war years discussion talking about some of the problem solving that occurred at the tunnel. We've already discussed drag cleanup. This is one of the test techniques that evolved in which all of the cracks and crevices would be covered by tape on the aircraft. The front end would be faired in with streamlined shapes, and then the engineers would pull a piece of tape off at a time, measuring the increment of drag that was produced by that particular protuberance or crevice. And in so doing, make suggestions on how to improve the airplane. In addition to cleanup, a great deal of work was done on how to maintain cooling of the airplane. Stability and control was a big area of work. You remember the F-4U Corsair incorporated a huge 1,800 horsepower engine, 13.5-foot diameter propeller, would have made the landing gear much too long, so they decided to bend the wings and get by with standard size landing gear. However, this airplane had such a powerful engine and such a high loading on the propeller that on carrier approaches, the upwash caused by this propeller rotating would cause the left wing to stall before the right. And the airplane had a vicious stall to the left. They could not operate out of carriers. When the airplane came to the full-scale tunnel, after much experimentation, they found that simply putting a small triangular spoiler on the other wing and causing it to stall prematurely was the answer to the problem. And not a great deal of maximum lift was lost that way, and the pilot was able to maintain control. So when you see a Corsair out on the flight line, remember that came from the full-scale tunnel. Another expertise that was developed was how to predict where compressibility would begin on an airplane. This is only a 100-mile-an-hour wind tunnel, gang. You're not going to get into compressibility in this wind tunnel. But by running at different speeds, the engineers were able to project where compressibility onsets might occur first. The P-38, as most of you know, incurred a fatal crash early in 1941. Kelly Johnson was the designer of this airplane. He wanted to get into the Langley 8-foot high-speed tunnel to check out what he thought was a compressibility issue. We were testing the XB-29, and he could not get into that facility. The airplane was flown here, one of the airplanes, and it was tested in full scale, drag cleanup, and they also did an analysis of where compressibility was beginning to impact the airplane. And as you might expect, it was in this wing center section area. Now, the picture you see there, the group at Langley actually revised the airfoil shape to be like the laminar flow series used by the P-51 Mustang in an attempt to delay the compressibility. And they also reshaped the canopy form as well. They were not adopted. Later, Johnson got into the 8-foot tunnel, and they came up with dive flaps to relieve the P-38 of its compressibility problems. Over on the right, a good example of what we got into out in the fleet, we found that under certain crosswind conditions, there wasn't sufficient hydraulic power on some of these airplanes to unfold the wings. So tests were done with several of the airplanes to be able to test that particular condition and improve the hydraulic system. One last thing I want to mention today in view of the recent news. One of the real issues the Navy had when they started testing airplanes in this wind tunnel was the cockpit environment. And lo and behold, F-22 issues. These were the first airplanes that the Navy had with enclosed cockpit canopies. And they had a vicious problem with carbon monoxide poisoning. Particularly the Brewster Buffalo suffered throughout its whole career with carbon monoxide activity. So every airplane that came in the tunnel, in addition to do aerodynamic testing, was also tested for the cockpit environment and how much and what the level of carbon monoxide was in the cockpit. Now, I want to talk about something today that was stimulated. It's an undocumented project, which I found extremely interesting. You all know that this week is the 70th anniversary of the Battle of Midway. When I started this book, I mentioned to one of the old-time mechanics, I'm writing the most detailed book ever written about the full-scale tunnel. And he calmly said, okay, Joe, don't forget about those tests we did on the Japanese Zero. I said, what? I've got every picture ever made in this wind tunnel. I've got a copy of the test log. There's nothing about a Japanese Zero test. Well, I subsequently talked to a few more people, and before long I found not only had a Zero been tested, but it was probably the most famous Japanese Zero of World War II. So let me tell you that story. It starts during the Battle of Midway. During that battle, the Japanese had sent 2 carriers, each carrying about 11 Japanese Zeros and 10 bombers, up to the Aleutian Islands as a diversionary tactic to try and draw our fleet away from Midway. And they attacked an army garrison at Dutch Harbor in the Aleutian Islands. This is a picture of the actual attack, and during the attack, during a strafing one of the Zero's oil lines was punctured by a ground fire. This is the actual airplane. You can see the smoke trailing. The result was the pilot and 2 wingmen decided to fly about 25 miles east to Akutan Island, where a Japanese submarine would be waiting offshore for anyone that was down during the attack. They took a look at the terrain on Akutan Island and thought they saw a nice, flat, grassy area. The pilot put down his wing flaps, his landing gear, and came in for a landing. It turned out this was a bog, and water was beneath all of that grass. The airplane flipped over on its back, killing the pilot. The wingmen wanted to destroy the airplane, but neither could bring themselves to do it, not knowing whether the pilot was alive or not. So they went back to the carrier, and the airplane laid in that state for over a month. Nobody saw it. Nobody acknowledged its existence. About a month later, a Navy pilot flying home with a PBY Catalina saw the airplane from the air, recognized it as a Zero, and needless to say, the Army and the Navy pounced on it. At the beginning of the war, the Japanese Zero was invincible. We didn't know how to fight it. We didn't know its properties in terms of design information, and any availability would be a tremendous boon to the United States. The Navy sent a rescue group to salvage the airplane. By the way, you can see the propellers weren't even bent. It did require some rework, but the propellers weren't even bent. The airplane was shipped down to San Diego at the beginning of September. The Navy worked 24/7 to get this airplane into shape under top secret conditions. A 20-foot high barrier was built at North Island around the airplane so nobody could see what was going on. The airplane was refurbished. It was painted in U.S. colors, blue-gray upper surface and a gray lower surface. The Japanese insignia was replaced with American insignia. There were two priority uses for this airplane. The first was find out what tactics we needed to fly to beat the airplane. The second was what it was its engineering properties. So at North Island, during the remainder of 1942, the airplane was flown against all of our fighter aircraft. The results showed, number one, not one of our airplanes could keep up with this airplane in a traditional turning dogfight. Its wing loading was way too low. It was not the way to fight the airplane unless you wanted to die. What was found, though, was at high speeds above 150 miles an hour, the ailerons became almost impossible to move. Furthermore, if the airplane went to negative G conditions, as in a sharp dive, the carburetor float would cut the engine off. So in addition, one other thing, it was found that the airplane could roll to the left much easier than to the right. So this information was quickly sent out to the fleet pilots. There are several World War II aces that remembered the briefings and in fact relayed incidents in which they saved their lives by knowing roll to the right, don't roll to the left, nose down, get up above 200 knots, and then do a sharp roll to the right. The Japanese did not know we had captured this airplane. Japanese historians today regard the capture of that airplane as equal importance as the U.S. victory during the Battle of Midway. So it was a tremendous boon for the U.S. intelligence. Now, here's the interesting story. In 1943, the Navy at Anacostia in Maryland said, okay, you've developed the tactics. We want some data on this airplane now. Fly it to the East Coast. The airplane was flown to the East Coast to Anacostia Naval Air Base, which was right outside of D.C. By the way, it flew cross-country and not one air spotter reported a Japanese zero over the United States. This is a picture taken of that airplane when it visited Langley. This is at Langley Field. The Navy flew it here because the experts here at Langley were worldwide recognized as being the tops in instrumentation field, and they wanted good quality instrumentation for their flight testing. It arrived on a Friday afternoon, in the afternoon, and the head of the wind tunnel, full-scale tunnel at the time, Abe Silverstein, went over to view it, and some arrangement was made, and I'm sure Walter Deal was involved, in which it was agreed that they could pull this airplane back over to the full-scale tunnel and test it. It arrived at full scale that evening. By the next day, Saturday at noon, it was under test. They did extensive measurements of aerodynamics of this airplane. By Sunday night, they pulled it back undercover to where it was on the runway. And at that time, they installed the instrumentation. This picture was taken after the instrumentation and nose boom and wing booms were put on the airplane. It was not flown by our pilots here. It was flown back to Anacostia by the Navy pilot, and at that position, it was evaluated during its flight. This was the most secret test done at Langley in World War II. There was no reports, there were no photographs made of that airplane in the tunnel. They even cheated on the wind tunnel test log and put something else in to give no indication that it had ever been here. The data obtained from the test were hand-carried by NACA courier to the Navy, and Walter Deal got his information that he was after. Remarkable piece of information. The summary of what this country benefited in terms of all the work that was done here at full scale was summarized by Walter Deal. Someone asked him, tell us about your relationship to Langley, the NACA, and what they accomplished. He says, I want to say one thing. The people at the NACA Langley full-scale tunnel saved this nation. He says the F-4F Wildcat was floundering around the sky at 280 miles an hour when Roy Grumman came in my office and said, Walter, they fixed the Buffalo. Can we get them to fix the Wildcat. He said a week later that airplane was in the tunnel at Langley. We got the airplane fixed and up to speed and got it out to Guadalcanal. He says what they did for the Corsair, for the Hellcat, and all of our aircraft made all the difference in the Pacific War. He said those people earned their money. Now, leaving World War II, I want to talk about other things that happened at the end of the war. When the war ended in Europe, the Germans, of course, had advanced jet propulsion and rocket propulsion. Alexander Lippisch was a German who designed the Me-163 rocket-powered fighter, which raised chaos with our bombers at the end of the war. In 1944, Lippisch was in the design process of a supersonic ramjet-powered fighter. This ramjet-powered fighter would be propelled by coal dust, since the Germans had very little in the way of propulsion fuels at the time. He had done wind tunnel tests on this delta shape that proved it was an efficient supersonic airplane. The ramjet had been tested above a bomber airplane. But what really concerned him now was this is a pretty unconventional shape. How will it land and take off? So they built this glider out of plywood, and it was almost finished when the Army captured it. It was finished by the Germans, and then it was crated and shipped to Norfolk and over to the full-scale tunnel for wind tunnel testing. Now, the reason for doing this, the Convair Company and others interested in supersonic airplanes at the time wanted delta wings on those airplanes. They had derived data from small-scale models and wanted to compare the results on this German airplane. When they tested the airplane in the full-scale tunnel in 1946 and provided the data to the industry, it was appalling. This airplane demonstrated 30% less maximum lift than the models were, which really concerned American designers. After much testing analysis, they came to the conclusion, if you'll notice, this airplane has a very bulbous, rounded leading edge, which for wings of that sweepback are just not applicable for low-speed conditions. So the crew at the full-scale tunnel replaced that leading edge with a sharp leading edge, generating what engineers call vortex lift, and dramatically increasing the low-speed lift capability of the airplane. The results were fed back to Convair, which gave them confidence to go ahead with their design of the XF-92 prototype airplane. When Chuck Yeager flew this airplane, as he usually did, he approached the landing pattern and, to the absolute angst of the engineers, decided to pull the nose of the airplane up as high as he could. The airplane was well behaved, and everybody, the sweat left their brow, and it proved that this delta wing shape indeed could be a shape of the future. Now, the interesting thing about this is the first application of swept wing, sharp leading edge activity, which of course has made its way through history to application to the F-16 and the F-18. So sharp leading edges in terms of low speeds can give you a great deal of lift, et cetera. Back at the tunnel in those days after the war, of course, there were no more propeller-driven airplanes. There was no more need for drag cleanup. And once again, the issue comes up, let's close the full-scale wind tunnel. Well, airplane shapes changed. Supersonics were the name of the game, swept back wings. This display was put up for one of the conferences, and in it you can see work going on a swept wing with boundary layer control slots on it, trying to get lift augmentation for low speeds. You can see the Lippisch glider back here, supersonic wing shape, and other displays, as well as rotorcraft. So for a decade, a great deal of that type of work took place at full scale. The tunnel then did a number of unusual tests, and these were quite dramatic. The Albacore submarine had been tested at small model scale. The results did not compare favorably with the actual testing of the full-scale vehicle. They needed a larger model, so they decided to test in the full-scale tunnel where they could simulate all the appropriate submarine water entry devices. In addition, the test in the wind tunnel proved that the thing was unstable. One of the main complaints of submariners were when they pushed the stick forward, the column forward to make this submarine dive, it continued to dive. It didn't want to stop. The test in the wind tunnel showed it was unstable, and they were able to correct that problem and make the Albacore a satisfactory device. In the 1960s, the space program began to look at alternate landing approaches for spacecraft on return from missions. And one which was of some promise would be the flexible flex wing, which would be stored on board, basically invented by Rogallo here at Langley. That led to a number of capsule application studies and also utility vehicles that might use a flexible wing, as shown under test here in the tunnel. The Custer channel wing was a very unconventional design in which the propellers were enclosed in channels and produced extremely high lift for short takeoff and landing, but was not adopted for further production. And in the 50s, we also tested a Goodyear inflatable plane, the idea there being that in the case of a downed pilot, you would pitch this vehicle out with in a stored parachute container. The pilot could inflate the airplane. It required pressures no more than bicycle pressures. Have a small engine stored within the crate, and you could take off and do a self-rescue mission. So a lot of unusual testing took place. The space age came on, and very quickly the Mercury capsule testing was done in the facility. There was a need for a Mercury procedures trainer, which was in that building as well. This is John Glenn doing his mission planning. We did testing of lifting bodies and reentry shapes. In December of 1968, the lunar landing training vehicle crashed in Texas. The pilot escaped without being killed, but Neil Armstrong was in the training process, and the issue was, could we get everything back together by the following June before they departed for the moon? Another one of the vehicles was flown to Langley and tested in the wind tunnel, where they determined the control problem, and the other vehicles were retrofitted. In the 1950s, another group took over operation of the tunnel. These people were oriented towards stability control, not aircraft performance or cooling. And they introduced a very unique free flight model technique, which was unique to this wind tunnel. This, you see, the model was flown with pilots located in remote positions within the test section. Part of the cable coming in was a safety cable, which was operated by an operator to pull the model from the airstream if it went out of control. But the other part of the cable brought in compressed air power, which was used to power the models, as well as the flight control signals from a digital computer. This thing evolved over a period of 50 years, and the Langley full-scale tunnel was the only one that continually conducted it, entertained the training of its personnel to be experts doing this job, and it saved the full-scale tunnel during the post-Apollo years. In 1971, there was a new director at Ames, Hans Mark. Ames was in great trouble at the time. There was great talk of closure of the Ames Research Center, and they were looking for work to do. Hans Mark went out on a tear to see what he could accommodate within the Ames facilities. One of his victims was the helicopter program here at Langley. Everything was transferred to Ames. We lost that program. The next subject to come up was, we have a 40 by 80 foot wind tunnel. Why do we need the 30 by 60 foot wind tunnel? And this technique, and furthermore, the commitment that was made to Langley to train and maintain it, won out. And we were able to bypass Hans Mark hunting section in terms of trying to close that tunnel. This technique itself was very useful in unusual configurations, that is, will it fly or not, and test for conditions that we couldn't do using computer technology. There are certain flow conditions that are not amenable to computer solutions today. And I want to show you this quick film clip that shows a hypersonic boost, highly swept configuration, flying at low angles of attack and then at high angles of attack to show you the kind of instabilities that we were able to identify in this type of a test program. Here you see the model flying at low angles of attack. The remote pilots will pull it up to a higher angle of attack, and these are self-induced motions. The pilots aren't doing this. The bottom line is such tests provide a warning that there might be a problem, and you need to design the flight control system to be able to accommodate those kind of motions. Typical of the free flight work that was done over in the tunnel. It was perfect for vertical takeoff and landing airplanes. God knows there were so many different concepts for vertical takeoff and landing. You scratched your head and say, would any of these work for vertical takeoff? And the free flight technique was an outstanding way of looking at that. Vertical tail sitters, the tilt wing approach. By the way, this was invented at Langley. The first tilt wing concept came from Langley. The most famous application for vertical takeoff and landing were free flight tests done for the Kestrel, the P-1127, which was the forerunner of the Kestrel and today's Harrier. And then I want to mention over here on the right an example of enduring research by Langley. John Campbell, the individual on the left, came up with the idea for short takeoff and landing of tilting the forward nacelle down, blowing exhaust up over the wing flap structure for additional lift. Didn't work in the 1950s because we had turbojet engines. The environment was too hot. But when turbofans came, this concept became feasible. Today's C-17 airplane uses that concept that came out of testing from the full-scale wind tunnel. The tunnel went through an era of testing supersonic transports. Today, it's fairly easy to design the lines for a supersonic transport, but there are still terrible problems at low speeds. Just a great deal of work that went into that type of activity. In the Vietnam era, the country suffered an alarming situation where we were losing military fighters to stall spin accidents. These fighters had been designed in the 1950s where the military said, we're not going to dogfight anymore. We're going to stand off, launch a missile, kill the enemy without engaging him. Well, when we got into Vietnam, we found that we were back fighting Japanese Zeros again. These small Soviet aircraft could outturn our airplanes, and worse yet, our air-to-air missiles didn't work. So we had a real problem. We had to put guns back on the airplanes and learn how to fly the airplanes without losing control. A series of airplanes, the F-4 being the most dominant, we lost over 100 F-4s during high angle of attack, strenuous maneuvering due to stall spin accidents. I want to show a picture from flight testing out at Edwards Air Force Base by the Air Force of an F-4. By the way, the test engineer on this job might be somebody you remember or know. It was Bert Rutan. He's actually flying in the chase plane on this test. This is an F-4 up at 30,000 feet, and the pilot will put it into a tight turn. This is a controlled condition, a test program being flown by a test pilot who knows he's going to lose control of this airplane. But as he, are you going to play with me? As he makes the turn tighter and tighter, getting to higher and higher angles of attack, the airplane loses, blankets the vertical tail and departs in yaw, and the pilot enters the first few turns of a spin. Here the angle of attack is increasing, the wings rock once, and off he goes. This test airplane was equipped with an emergency spin recovery parachute, thank God, so he was able to break the spin by releasing the parachute. Now, Luad, I'm running way, way over time, I think. So I'm going to jump way ahead and apologize. I think that's only fair. The people in the full-scale tunnel and also at the 7 by 10 foot high-speed tunnel at Langley attacked the F-4 problem in fervor. We ended up with a fix for the problem, which were these leading-edge slats on the airplane. If you're ever down at the Virginia Air and Space Center, take a look at the leading edge of that wing. That came from technology advancements here at Langley in the wind tunnels and made the airplane problem go away, essentially. After the work with the F-4, all of the emerging aircraft came to Langley for free-flying tests. These tests weren't just flying models. These included measuring aerodynamics, putting them in piloted simulators, analyzing stability, developing control systems together with industry and DoD. And this is just a few, but every fighter airplane since the F-4 went through the testing, including the F-18 Super Hornet and the F-22 as well. We started a technology program to further develop new technologies that pilots could use for high angle of attack, including taking a look at thrust vectoring, which had been used on rockets for years for control. In our examination in the full-scale tunnel, we used simple deflectable pedals behind the engine for control augmentation for high angle of attack. That work was the focus of what led to the acquisition of an F-18 for NASA research purposes and a pedal-type system put on the back of the airplane to address the question of, if you had thrust vectoring, how much difference would it make in air-to-air combat? We also took a look at fold-out fins on the forward part of the fuselage to control the strong vortices that were shed by these pointed noses for further control augmentation. If you're down again at the museum, this airplane is down there. The results were extremely impressive. I want to show a brief film showing what thrust vectoring can do for aircraft. This is a supersonic version of the F-16. It was known as the F-16XL. This is the airplane in its original configuration, which was unacceptable at high angles of attack because of strong vertical flows up on the forward part of the wing. We implemented the airplane with vectoring vanes in pitch and in yaw to demonstrate just how effective this approach is for fighter airplanes. What you're going to see is a series of flight tests in the full-scale tunnel. First, with thrust vectoring off, as I mentioned, this airplane was very unstable. This number here is the angle of attack of the airplane. And the pilots are lowering the airspeed, increasing the angle of attack. And when the airplane gets to about 20 degrees, that safety cable pilot earned his money. This is with thrust vectoring on. Take a look at the angle of attack. Here's where we were in the last movie. The airplane is completely controllable. And while we're at it, let's just increase the angle of attack to twice that, up near 40 degrees. And since we're feeling so strong and vigorous, we'll go ahead and increase the angle of attack now to 60 degrees. So a vivid demonstration of how powerful these controls are on aircraft where the aerodynamic control services have basically pooped out and just aren't doing anything for the maneuverability of the airplane. I think the good Lord's sending me a message, Lord. He's not going to let me get this. Can't advance to the next chart. That activity in thrust vectoring is a good example of how research gets applied to real airplanes. This shows the NASA implementation of those simple vanes, obviously not a production version. This is the emergency spin parachute we carried with the airplane. And we took the cheap way out. Rather than building new engines, we decided to put the control actuators on the outside of the engine. A cheaper way to approach this. Again, with the primary purpose being, here's what you can do with an airplane if you have thrust vectoring. That technology and others in other organizations at Langley, particularly the 16-foot tunnel, fed its way into the F-22 Raptor, which of course is equipped with vectoring, at least in one axis today. In the 1990s, several things happened. NASA got a new administrator by the name of Dan Golden. There was great pressure on NASA to augment its space station and shuttle funding, and the decision was made in 1995 to retire the full-scale tunnel. The staff that worked there was moved to other locations with the mandate that, quote, continue your work, but in other places, use other wind tunnels to what you did. Center Director Paul Holloway worked an arrangement with the Old Dominion University to let them become new managers of the full-scale tunnel. This is Dr. Jim Cross, who was the chair of the engineering department at Old Dominion when he took over the full-scale tunnel. And to show the relative anxiety between NASA and ODU, the mandate agreement said you will not test aerospace-related projects, which left Jim in a real quandary. Okay, what are we going to test to make money on this facility? And bless his soul, he went out and championed the NASCAR community. He went to Daytona, he went to all the big races. Most of the NASCAR community never heard of the full-scale wind tunnel, didn't even know it was here at Langley. But they quickly proceeded to enter the facility on a fee-paying basis. Over 50 NASCAR teams came to the tunnel. Of course, great proprietary information in terms of even identifying who they were. The activity at the tunnel grew. Ground transportation, ways to minimize aerodynamic drag of trucks, worked in the academic world in terms of applying computational fluid dynamics for ground vehicles. And after a few years of this, NASA finally relented and let ODU back into the airplane testing business. This is an example of one of their activities. Good current day question. Suppose you have an unmanned aerial vehicle, a military vehicle, flying in formation. How does one assess the relative stability of the vehicles? And also, how do you refuel one of these vehicles? So they did quite a bit of work during the ODU years. A highlight of the ODU years. This I took from a 1945 newspaper here at Langley, 1945. And it was a cartoon in which the person is saying, oh, that flies through every year on Wilbur Wright's birthday. Obviously, the artist was depicting the full-scale wind tunnel, tongue-in-cheek. Little did they know that it would really happen. The Wright experience, you may know, was led by a retired American Airlines pilot, Ken Hyde, with the objective of recreating as accurately as possible the Wright brothers' gliders, propellers, and airplanes, and dislodged all those secrets that the Wright brothers kept. They didn't keep records or documents. They were scared to death somebody would find out what they did. Nonetheless, Ken and his team, through a series of experiments, actually hand-built with great skill a series of Wright vehicles. The test started with propeller testing in the tunnel, and one of the results from the hand-built versions of the Wright propellers, they had amazing efficiency. These propellers were 80% efficient. Before the testing, the world thought, well, 70% at best, but they were very efficient. The first thing was done was to go through and test the gliders that the Wrights flew before their flyer. In 2001, they tested the 1901 glider. The Wrights were very meticulous in terms of the data they obtained at Kill Devil. This glider, when they flew it, they maintained it had a lift-drag ratio of 6. When the glider was tested with the most accurate geometry the Wright Experience team could come up with, only showed a lift-to-drag ratio of 3. And this caused utmost chaos and trauma of what was going on. They rechecked all of the glider geometry, and then Ken Hyde remembered reading something about the Wrights applying some type of coating to the linen on their glider. So the team put wallpaper paste and coated the linen with that. The test results showed a lift-to-drag ratio of 6, in agreement with the Wright brothers. They also tested the 1902 glider to further along the information. And then finally, in 2003, they were ready to test the actual flyer. This was a vehicle, you'll remember, that was taken down to Kitty Hawk. It flew twice during an encampment before the December 17th anniversary attempt. But during that attempt, you'll remember there was a still wind, no air. They had a bulky engine, so the flight was basically unsuccessful. Since that time, Ken and his people have built 3 other versions of this 1903 fighter. The original, this one, is in the Henry Ford Museum up in Detroit. But other museums have also had versions of it built. Now, after all this excitement, we entered the 2009 timeframe, and the pressure throughout the government to reduce the number of facilities became extremely great. Not just for NASA, but for the Air Force and its operations. And as a result of that pressure, this is a listing of what happened nationally to our wind tunnels. In 1993, there was a total of 60 government wind tunnels spread throughout NASA and the military, of which 39 were NASA facilities. 4 years later, that number had been reduced to 39. NASA had lost or retired 14 tunnels. And in 2006, NASA's number had come down from 39 to 16. So there was tremendous pressure to reduce the tunnels, and one of the candidates was the full-scale tunnel. The decision was made at that time that the tunnel would be closed at the end of 2009. The last test in the full-scale tunnel, September 2009, was the Boeing, Air Force, NASA blended wing body, or X-48C. This is a remotely controlled airplane. It's being flown out at the Dryden Flight Research Center. Futuristic, with great potential for a future green airplane. Burns extremely less fuel and reduced noise as well. So with that, the tunnel was closed. The demolition began in December of 2010. This picture just rips my heart out, but the demolition process took place with the help of the Army Corps of Engineers through a contracting mechanism, which saved NASA 50% of the estimated cost of demolishing this building, as well as a 16-foot tunnel, as well as the 8-foot tunnels over on the east side. The demolition started, and by May, the end was in sight. This is the last structure going down on the facility. Finally, in July of last year, this is the vacant spot where so much history had occurred, where all those pioneers of aviation had visited, where all that historic work of World War II had taken place, and it's all into history now. It's not forgotten. The public can access a website via a Langley site in which you can access the history, all the 3,000 photographs that were taken in the full-scale tunnel, all the documents, the important reports that were written, the tunnel test log. You can take a virtual tour of the facility, and there are over 40 video movies, like I've shown you today, of activities that went on in the tunnel. That is the URL site for the website. Be glad to pass it on for anybody who's interested. All of these aircraft that you see in air shows today, it's interesting that all were touched in one shape or form by the full-scale tunnel, either in terms of full-scale airplane testing or model testing, whether it's a Navy air show or an Air Force show. And I think that's remarkable that we've been able to maintain that. If you go down to the downtown museum, all of these airplanes on exhibit were touched by the full-scale tunnel in one shape, form, or the other. Before the demolition, Langley did extensive looks at the artifacts available in the full-scale tunnel. The Smithsonian Museum visited, and we have donated to the Smithsonian one of the Toledo scales, a complete propeller set, propeller hub, and a spinner from one of the propellers. The game plan for those artifacts is to be displayed at the Smithsonian National Air Space Museum, downtown Washington, in the mall, in their Milestones of Flight exhibit. I can't say how impressed I am that the Board of Governors of the Smithsonian decided that this facility warranted a place in what is the altar of aviation. It will be displayed as you enter the door from the mall entrance. It will the constructed propeller will be displayed on this wall, and an appropriate exhibit as to the background and history. But take a look at the companions that will be there. The P-59 that happened to be there as the first jet, the X-15, the Spirit of St. Louis, Bird Rutan's Spaceship One. Quite a landing place for an old wind tunnel built in the 1930s to test biplanes. So very enthusiastically looking forward to that. NASA and the museum are currently in negotiations about the exhibit and how it will be done. This wall in the museum is not a load-bearing wall, so they're going to have to construct some type of supporting display and exhibit there. That's to be discussed. The game plan is to have the exhibit available by the end of next year, probably December of 2013 or early 2014. Now, my last statement gets back to the book. The book was submitted to headquarters in March, and the NASA game plan is to delay printing of that book until this exhibit opens up at the museum and an appropriate dedication ceremony can be had. So I'm sorry to report that, but at least we'll have the information in great detail for the future of the activity. That completes my very overtime discussion of what is one of Langley's historic facilities. All you new people, hope you've heard something today that you can filter into the back of your mind. When my good friend Dick Whitcomb read several of my books about the history of Langley. He said, Joe, this is a tremendous undertaking, and it's nice to document the technology that we did. What is important for history is to read these books and understand the mechanisms, the relationships that let these things happen. It's a lesson for management. It's a lesson for all the young people. So with that, I'll close, and I'm sorry I ran so far over that.
Thanks so much, Joe, for a wonderful, wonderful lecture, obviously, as I knew you would. And just a small token of our appreciation.
I appreciate it.
Memento of aircraft here at Langley. So thanks again, Joe.
Thank you very much, and thank you so much for staying with me. I apologize for running over. I hope all of you will have a chance when the artifacts are displayed up at the Smithsonian to visit it, and I hope that the museum's exhibit is worthy of what this wind tunnel has really contributed to the United States. Thank you.
So after many years of illustrious years of leading the full-scale tunnel, the vertical spin tunnel, the drop model test technique in cutting-edge research and technology development that was nationally and internationally recognized, Joe moved on to other important leadership roles in flight research and in systems analysis, where he was equally successful. And for all these accomplishments, Joe received numerous awards and has presented invited lectures all over the world. But after a very productive 36-year career, Joe retired from NASA and started a second career doing historical research on Langley. And the result of these endeavors are 7 fascinating books, NASA publications on a variety of aeronautics topics. And his latest book that he's currently working on is the basis for the lecture that we're all about to hear, with the title as you see there. And I know we're all very much looking forward to reading this book and to hearing Joe's lecture today. So without further delay, let me turn the podium over to our speaker, Joe Chambers.
Thank you, Luad. Everybody hear me? He didn't tell you the part that I won all the card games. That's why he was so great with his comments. When Gowdy called me, the tunnel was visited by many of the most famous people in the history of aviation and others who were awestruck by its massive size. The full-scale tunnel was demolished last year, but will live on forever for its impact and contributions to aerospace technology. About 3 years ago, the opportunity was presented to me to write a book about the history of the full-scale tunnel, which, of course, I completely leapt at, and was able to get into archives, old reports and things that had never been really analyzed, discover a lot of information that had never been documented. And what I'm going to present today, for those of you not familiar with the facility, I think will be impressive. For those of you that are familiar with the facility, I'm going to surprise you with some things that I found out that happened there that you don't know about. So I'm hoping that you'll be entertained by this. The book draft is completed. It's up at NASA headquarters now in the queue waiting for printing. There's over 400 photographs, close to 500 pages, and several hundred references for those that want to get into more detail relative to the facility. At this time, the book is not published, and I'll close the presentation with some comments on the projected schedule for its release. The presentation, as Luad said, is based on selected excerpts from the book, and at the onset, I want to apologize on 2 counts. The first is my comments are going to be very brief in view of keeping us constrained to our time today. And the second is, if you're a fan of the full-scale tunnel, I apologize if I don't mention your favorite topic. The next slide is going to show the outline of the presentation. What I'm going to try and do here in the next hour is to discuss how this tunnel came to be in terms of the politics and mechanisms that originated the tunnel and some of the birthing pains that it went through as it went into operation. We'll spend time talking about the war years and World War II when it served the greatest generation and it's probably its greatest legacy. Talk about the post-war years and what happened immediately after World War II. And after the Sputnik event, how this old wind tunnel designed to test biplanes fit into the nation's space program. In the mid-90s, NASA declared the facility to be non-relevant to its mission, and it was an arrangement was made for the Old Dominion University to operate and manage the facility. I'll discuss some highlights of those years, and then I'll close talking about the end of the line in terms of the final closing of the facility, the demolition of it, what we've done in terms of artifacts from the tunnel and where and when they will go on public display. And then I'll talk finally about the book and when you can expect to see the book. During rehearsals, this ran about an hour. I hope you'll stay with me during that hour. I promise to keep you entertained. You keep your eyes open. The story of the full-scale tunnel starts with a deplorable situation in the United States. There was almost total lack of interest in aviation in this country, the country that invented heavier-than-air flight. When World War I started, the European nations, France, Germany, England, all had over 1,000 aircraft. The United States had 23. Alarmed by this whole situation, a number of notable scientists, Alexander Graham Bell, Charles Walcott, who was the secretary for the Smithsonian Institution, and others, advocated strongly to Congress that we needed to do something in the United States to organize the progression of aviation. In 1915, without any great ado, Congress approved the formation of what was called the National Advisory Committee for Aeronautics, or the NACA. And with the establishment of that committee, it was to be manned by a group of 12 presidential appointed individuals who served with no salary. And in this day and age, I have to say they had no year-end multi-million-dollar bonuses either. The facility, a research facility, was also an option when they formed the NACA. Well, it didn't take very long for the members to say, we need a research facility. So in 1917, this area was acquired by the War Department for a research laboratory. Now, tonight I'm going to be talking to people who aren't familiar with the background or the location of these facilities. So I'm going to present this orientation and said, Joe, would you mind coming out and talking about the full-scale tunnel? I said, don't throw me in that briar patch. No, please don't do that. This is my favorite topic, of course, and I want to thank the Colloquium Committee for inviting me out for this, and I hope you'll enjoy the presentation. It's pictures, it's movies, there's no equations, there's no word charts, so enjoy. This year, the NASA Langley Research Center is celebrating its 95th anniversary. And as Langley continues to undergo inevitable and dramatic changes in the missions and the culture, the facilities, it's extremely appropriate, I think, to reflect on the great legacy of this research center. And today we're going to talk about a facility that certainly is embedded in the most intimate history of aviation in the United States. The full-scale tunnel went into operation in 1931 as the world's largest wind tunnel. It was the first tunnel capable of testing powered full-scale airplanes. It completed its last test program in September of 2009 after almost 80 years of continuous service to this nation. Over its lifetime, I counted a total of 1,564 tests of individual test subjects, many of which were critical to the interest of the United States, both militarily and in the civilian world. Housed in a building longer than a football field,